Okay, so the recording is started. So welcome back to SI. Hopefully everyone's had a good start to their week, right? And I'm sure for you guys kind of feel the semester really getting underway. So before we start with going over the challenge problems for Monday night sessions, there's just two little points that I want to talk about. So the first thing is a student actually asked me via email to kind of just talk for about units of K for a second. And so I responded to them, but also for anybody else that has confusion on how to find the units of K, right? So remember that rate will always be measured in molarity per time, right? And time can be seconds, minutes, hours, right? It just depends on the problem. Okay, but the more important part for us is that the numerator has to be molarity, okay, or big M. Sometimes you'll see moles in the numerator and liters in the denominator, right? Remember, moles per liter is a molar. So you might also see it in terms of moles per liter times time. Okay, but how do you figure it out? So let's use an example of a second order reaction, right? So the rate law for this is rate equals K times our reactant A squared. Okay, so again, let's remember that the units of rate always should be molarity per time, right? And our unit for A, our concentration of some reactant, is going to be molarity, okay? But remember that because this is second order and the concentration of A is squared, we also have to do the same to the units. Okay, so the units associated with A would actually be molar squared. And again, that's because it's second order, the concentration of A itself is squared. Okay, so kind of looking at this expression, I kept K as K. I would ask myself, what do the units of K need to be so that when I multiply it by molar squared, it gives me the units molar per time. Okay, so for a second order reaction, the units of K would be 1 divided by molar times, I'm still in the denominator, times whatever unit of time you're using. Okay, so 1 over molar times time would be the units of K in this example. Okay, so I think using that logic and thinking can help you kind of start to become more familiar with this. And what I'd recommend is just work on the units of K and start with 0, first, and second ordered reactions. Okay, and once you get familiar with how to derive the units of K for 0, first, and second order reactions, then start to get into your abnormal reaction orders. So, okay, what would the units of K be for a fifth order reaction, an eighth order reaction, so on and so forth. Okay, the other portion that I want to talk about, just because I've received a lot of emails about it, is anything having to do with your lab. Lots of people are asking me for help on the lab both last week and this week. And I just want to make it clear that I'm not associated with lab at all. I don't have the lab manual. I don't review the background for the lab, nor the procedures of the lab, the conditions, or the goals. So I really know nothing about lab besides what I know from taking this course 4 years ago, which in terms of lab, I remember very little. But if you do ask for help, I always will try my best. So if you do want to meet with me about something lab related, I will be happy to do so. But I'll probably make sure that you're aware that I'm not your best resource, right? Your best resources are to reach out to your TA or one of the professors. And especially on the last lab, the vapor pressure lab that I'm sure many students struggled with, many people brought that to my attention, that was something people were struggling with and asking for help. And so I actually reached out to Dr. Katie, asking what resources were available to students in relation to help with lab work, because I wasn't sure with our adjustments to COVID if the resources that were in place are still available for you guys. And so I was trying to work out something with him. And what he kind of responded with is that the lab last week was really difficult. So the fact that many students had questions wasn't surprising, but that to remember that the professors host Q&A sessions during normal lecture times, like live Q&As. And so one thing that he really recommended is if you have questions, especially having to do with lab, Obviously, your professors are probably the most equipped to answer those questions, and that definitely make sure that you're utilizing those Q&A sessions, because I know he says that typically only 20 to 30 students come to those, but as you can imagine, small groups of 20 or 30 with the professor themselves can be a very beneficial resource. So I just want to touch upon that, and don't forget about that resource. But yes, if you do want to work with me on lab, I'm happy to do so. Just realize that I don't really know anything about it. I can only talk about it from a general chemistry standpoint. And so kind of be patient with me if you're looking for my help on that. Okay, so jumping into the challenge problems for Monday, right? So question 1 is, what is the rate constant for a first order reaction that has a half-life of 30 minutes? Okay, and so what I want to turn your attention to is the options here, right? So not only do we need to calculate what K, or our rate constant, is, but you might notice that many of these options are the same in terms of their value, but differ only in terms of their units. Okay, this is why it's extremely important to have the skill to be able to derive your units of K, right? Because this type of problem right here, I believe, was basically directly on my exam 4 years ago, and it has appeared since. Okay, so it's really important in this chapter to learn how to derive the units of K. Okay, so for a first order reaction, our half-life, which is 30 minutes in this case, will be equal to 0.693 divided by K. Right, this numerator value is actually equal to the natural log of 2. And if anybody wants me to derive that later, I'm happy to show people that derivation. But basically, 30 minutes is equal to log of 2, which is 0.693, divided by K, our rate law constant. We solve for K, and it comes out to 0.0231. And this is a first order reaction, and you can kind of see me doing it down here. In order for my units of rate to be molar per minute is just the time that we're using here. In order for that to be true for rate, my units of K need to be 1/minutes. Okay, and so the answer to 1 should have been D. Moving on, number 2, use the rate law below. The concentration of A is tripled, while the concentration of B and C are cut in half. What is the effect on the reaction rate? Okay, so you might notice when looking at your rate law that you don't see a concentration of B. Okay, the reason for this is that the order of B, reactant B, is 0, right? So no matter what the concentration of B is, because it's 0 order, it won't affect the rate. Okay, so only my changes in concentration of A and C are going to affect my rate here. Okay, and so basically in the problem, we're told that we are tripling the concentration of A, which reactant A is first order, meaning if we triple the concentration of A, we're going to be multiplying the reaction rate by 3. Okay, so I'm going to write 3 down here. And then our other change, right, we're going to ignore the change in concentration of B because that won't affect our rate due to it being 0th order. But our other main change is that we cut our concentration of C by half, right? So our new concentration is half what it used to be, and reactant C is second order, meaning if we decrease our concentration of C by 1/2, the effect on the reaction rate is that it'll actually be 1/4 as fast, right? Which is 1/2 squared. Okay, and so what I do is I multiply these two changes together, right? The reaction rate should be 3 times as fast based on reactant A, and 1/4 as fast based on reactant C. And so making both of those changes will cause my reaction rate to be 3/4 as fast, which was option C. Okay, and this is very similar to, again, one that you'd see on the exam, where you're given a couple of changes. The changes won't be too funky. It'll be pretty similar to this. And based on increases and decreases in concentration, you say what the new rate would be in relation to the old rate. Okay. 3, so this one, again, very similarly, if we look at the actual value of K, right, these are all rate laws. If we look at the value of K, they're all the same. So really what they're assessing here is, do you know what the units of K should be and what would the rate law be in response? Okay. And so here you're told that we make a plot of the concentration of A versus time, and that a straight line results with a certain slope, right? So remember that when we do a graph here, whenever we graph the concentration of A versus time and we get a straight line, you 100% know with absolute certainty that that has to be a zero order reaction, right? Because if you graph a first or second order reaction and you do concentration in A versus time, you wouldn't get a straight line, right? You only get a straight line if it's zero order. Okay, so we know it's a zero order reaction, and our slope is negative 0.864. Okay, now when you graph a zero order reaction like this, our slope is equal to negative K. Okay, so this means that K itself is just 0.864, right? So that's how we know that value. And again, it is a zero order reaction. So what would the units of K be for a zero order reaction? Well, it would be molar per second, right? And I know it's second just because that's the only time option given in this problem, right? Molar per second. And molar is really moles times liters to the negative first times seconds to the negative first. Okay, so the answer to this should have been A. And you'll notice I didn't put times the concentration of A, because the power of that, it would have been, it's zero order. So it would have been concentration of A raised to the 0, which is 1. And so I ignore the concentration of A here, right? You don't need to write it. Okay. So number 4, there was actually a mistake on, so I apologize. I believe the original question asked for the rate of the reaction when you return, which I will tell you how to do. But you'll notice that the multiple choice options were all a concentration, okay? And so what I meant for the question to be was, after 72 hours, what is the concentration of reactant? Okay, and this one is actually a very challenging problem, okay? It doesn't really tell you a rate. All it says is that when you go from 2.7 molar down to 2.18 molar, your rate decreases by 35%, okay? And then they tell you an initial concentration and a half-life, and then after 72 hours, what's the concentration? And so those first two sentences, and I did this in a very challenging way, so if you didn't register this, that's completely okay. That first sentence or two was really one of those table problems that we've been doing, right, to solve for reaction order and our rate law. Okay, I just did it in a verbal form, right? So what I'm going to call trial 1, I'm going to say that my concentration of reactant is 2.7 molar. And in trial 2, or time 2, my concentration of reactant is 2.18 molar. Okay, now what is my rate of reaction? Well, I wasn't actually given a defined rate. All I said was that we have a 35% decrease in rate when we're at the 2.18 concentration for A. And so I'm going to denote my rate of reaction as X for my 2.7 molar trial, which is trial 1. And then trial 2, my rate of reaction would be 35% less than that, which would be 0.65 times X. Okay, now I'm going to plug in this data from these two trials, just like I did beforehand, with putting the information in trial 1 in the numerator, in trial 2 information in the denominator, right? So 2.7 divided by 2.18 raised to the X power is equal to X divided by 0.65X, right? And so when we do this division of these rates, right, that quotient comes out to about 1.5. And when we find the quotient of our concentrations, it comes out to about 1.24. Okay, and again, remember that that's raised to whatever the order is for this reactant. So when we solve for X, when we solve for the order of this reactant, we find that X equals 2, meaning our reactant A is second order in nature. Okay. Once we have that, we can choose the appropriate half-life equation, right? So we're told our half-life is 4.88 hours, okay, which will be equal to 1 over our original concentration times our rate constant K. Okay, and hopefully, I maybe didn't write the question as well as I could have, but hopefully you realize that this initial concentration value should have been the 2.25 value, 2.25 molar that was given in the problem, along with the half-life. And we can find that K should be equal to 0.091, and if you wanted the correct units on it, it should be 1 over molar times hour. Okay, now that we have our K, our rate law constant, right? We have our time, because they give that in the problem. They say, what's your concentration after 72 hours? Okay, and we have our original concentration, A naught, which was the 2.25 molar given in the problem, right? We have all the information that we need in order to solve for the concentration of A. Okay, and when you go through this math, you will find that the concentration of A should have been 0.143 molar. Okay, so that was option C. Okay, now if you saw the original problem, I accidentally asked for the reaction rate, right? And so if you wanted to solve for the reaction rate, you would do this exact same step, all of this that I did, and then you'd find the concentration of A, which is equal to 0.143, and you'd plug this value along with your K that you found above into your rate law equation, right? So this is a second order reaction, so rate equals K times A squared. And so rate equals 0.091 times the concentration of A, 0.143 squared. Okay, and when you do that, that would give you the reaction rate after 72 hours. Okay, this problem was really difficult. So are there any questions on this one or any of the ones we've gone over before it? Okay, I am going to go on, but if you're taking your time to type a question, I'm happy to come back to it. Right, so this one's kind of your classic. This is definitely, it's similar to the one before. Number 4, it's an integrated rate law question, but this one's much more straightforward, right? So you didn't have to use kind of like the chart problem way to find that it was a second order reaction. This time I tell you, you're told the half-life, and you're told an initial concentration and a final concentration, right? So here it's more just plug in and solve, right? So our half-life is equal to 236 seconds. It's a second order reaction, so this is our formula for half-life. We're told what our initial concentration of A is. It's 0.00956. And so by manipulating this equation, we can find that K, our rate law constant, is about 0.443. And again, these would be the units associated with that. Okay. Next, I'm going to write my integrated rate law for a second order reaction, right? So 1 over the concentration of A equals our constant times time plus 1 over our initial concentration. And so in this problem, again, we solved for K above using our half-life, and we're given our current concentration, or kind of our final concentration, at 0.00543, and we were given our initial concentration as well. And so again, here through algebraic manipulation, we can solve for time, and time was about 180 seconds, right? So what that's saying is it takes 180 seconds for our concentration of reactant to go from 0.00956 down to 0.00543. Okay, and then I believe there's 2 more to go over. So number 6, so you have 1,000 apples that contain 600 grams of potassium. About 1.17% of this is radioactive, which decays in first order fashion, and they give you a half-life. and they say how long will it take to reduce the amount of the radioactive potassium to 1 milligram, right? So again, very similar to the last problem. This time we're just doing an integrated rate law question with first order reactions. And again, you know it's first order just because I told you. Okay, so we have 600 grams of potassium in total, and we're told that 1.17% of that is the radioactive isotope, right? So 1.17% in terms of decimal form is 0.0117. And so by multiplying these together, we find that we have 7.02 grams of our radioactive isotope. Okay. Now, our half-life equation, so T1/2 is equal to the 1.5 or so times 10 to the 9th years. Again, this is first order reaction, so our half-life equation is that our half-life is equal to 0.693 divided by K. And we can rearrange this to solve for K, which comes out to 4.56 times 10 to the negative 10th, and the units on that should be 1 over years. Okay, now again, this is a first order reaction, so I'm just going to write the integrated rate law for a first order reaction, which is the natural log of A equals negative KT plus natural log of our initial concentration of A. Now, the equation I wrote below it is the same exact equation that you see above. Okay, what happens is I just subtract the natural log of A naught from both sides, and if you know your log rules or natural log rules, right, if you subtract natural log of A minus the natural log of A naught, or original A, it's the same thing as doing the natural log of A divided by A naught. Okay, so we'll often put it in this form. And again, that's just log rules. Okay, so either hopefully you know your log rules or just kind of memorize that's something that you can do. Okay, so natural log of A divided by A naught is equal to negative KT. Now, 7.02 grams is how much of this radioactive isotope we have, which I convert to milligrams, and it's 7,020 milligrams. Now, for this section, natural log of A divided by A naught, although you typically see it in terms of concentration, right, we're doing division here. So the units, as long as they're the same, they don't really matter, okay? And so here, I can actually plug in my ratio of milligrams, right? And again, it's because you can really only do this with first order reactions because you're doing division, okay? And so instead of having to plug in concentration units here, I can just plug in the ratio of my masses, okay? So my concentration of A, kind of my final concentration, is 1 milligram. My initial concentration of A, which is my radioactive potassium in terms of milligrams, is a little over 7,000. And so when I solve for the ratio between these, it's 1.425 times 10 to the negative 4th. Okay, so I do the natural log of that ratio that we just solved for is equal to negative K, which we solved for above, times time. And when we solve for time, it comes out to 1.94 times 10 to the 10th years. Okay, so the big key here is that in first order reactions, you can rearrange your equation like this, and you actually don't need concentrations to plug into first order reactions because it's a ratio between them. So as long as they have the same units in the numerator and denominator, you can plug that decimal or fraction in and it will give you the answer. Okay, and lastly, so this is a very, very challenging problem, so hopefully you tried it on your own. But basically you're given there's 3 reactants that contribute to the reaction rate, right? A, B, and C. And it's a classic chart problem where not only do you have to find the rate law, but once you find the rate law, you have values to plug in to find the reaction rate. Okay, and so whenever you're trying to find a new or novel trial, right, if you ever have to do that, here are the steps, right? So I'm going to be referring to these steps. These are the ones I kind of came up with last session during our activity. And so I'll kind of just be making references to these. So I wanted to have them on here. Something that I wanted to note before kind of going into these steps to create a novel trial. um, always find whatever orders you can before making a novel trial, right? So here, I believe you can use the chart to normally solve the order of reactant A and B, okay? And so I would say do that first and then kind of do this process to find in this problem what the order of C is, okay? And so that's what I do, right? So to find the reaction order of A, I use experiments 2 and 3, and I put the information of experiment 3 in the numerator. I eventually solve for my reaction order and find that reactant A is second order. Okay, I do the same process for B. Here I use experiment 1 and 2 because that's where only the concentration in B changes, right? You want the other things to stay consistent. And when I solve for my reaction order, it comes out to fourth order. Okay, are there any questions? I know I kind of skipped over that very, very quickly because we've been doing these a lot. Are there any questions on this before I jump to the next slide where we really look at how you would find the reaction order for C? Okay, so I will go to the next slide in just a second. The only comment I want to make before going on is that this is definitely much harder than you would see on the exam, right? If you want to see kind of an exam level difficulty question where you have to make a new trial, I would say look at the one that we did on Monday. Yeah, the first time I brought up making a novel trial, which was in Monday's session, that example is the same difficulty as you would see on the exam. This one I anticipate being much, much harder. Okay, so I kind of write the steps and how they align with those steps I kind of gave you at the very beginning. And so step 1 is to identify a trial, right, that you just want to start with. And typically you want to start with trials that have low concentrations, right? That's what it says in parentheses. Pick a trial with, typically you want them to have low concentrations. Now in this case, I chose trial 2. And I'll explain in just 1 minute why I didn't choose trial 1. Okay, so trial 2. Okay, step 2, and I just wrote the information from trial 2, right? So these are my concentrations associated with trial 2. Step 2, identify a trial with different concentrations for A or B, right? Not both. A or B should change in concentration here, along with C. Okay, so C has to change in concentration, while A or B, only one of them can change in concentration, right? So if I chose trial 1 originally, let me go back so that we can all look at this data, right? If I chose trial 1 and compared it to trial 4, right, which is what I'm doing, trial 4 is the trial that I pick in step 2, right? We can see that the concentration of A changes, my concentration of B changes, and my concentration of C changes. Okay, that's why I didn't choose trial 1 in that first step. Okay, instead I chose trial 2. When we compare trial 2 to trial 4, right, our concentration of A changes, but our concentration of B stays the same, while our concentration of C changes. Okay, and so that's why I chose in step 1, trial 2, and in step 2, I chose trial 4, right? Because we need the concentration of C to change, and we need the concentration of A or B to change, but not both, okay? Because if not, there's just too many variables changing. Actually, you might be able to do it from trial 1 now that I'm thinking about it. It is possible. So I'll actually investigate this further and see if you could choose trial 1 in step 1. But anyways, that's kind of the reasoning why I personally chose trial 2 and 4. Okay, but if you can solve it using trial 1 to trial 4, I'll bring that to the next session to show you guys that. Okay, so now let's look at step 3. Okay, so to make our novel trial, you're going to change the concentration to match with trial 4, right? The trial that we identified in step 2. Okay, and that's the only concentration that we're going to change in our novel trial. okay? So in our new trial, right, compared to trial 2, the original one we chose, I'm going to change my concentration of A so that it matches the concentration in trial 4, but I'm going to leave my concentration of B and C the same as they were in that original trial from step 1, which is trial 2 here. Okay, so again, I only change my concentration in A, while B and C I stay the same. Okay, now from trial 2 to my new trial, my concentration of A tripled. Okay, and I know that the reactant A is second order. So if my concentration of A tripled in its second order, that means my reaction rate should increase by 9 times what it was. Okay, so to find the rate of my new trial, I'm going to take my rate from trial 2 and multiply it by 9, okay, which I get here. Okay, lastly, I can now use trial 4 and my new trial to solve for my reaction order of C, right? Because my concentration in B of and A are the same from trial 4 to my new trial. It's only my concentration of C that changes. So I plug in the data from those two trials, and I eventually find that C is first order. Once I know the order of each reactants, I can write the rate law, right? From here, you can plug in data from any trial. I chose trial 1, but again, any trial is equally as good. I plugged in the data for this and solved for K, which came out to 0.0422. And the units of this, to be correct, should be 1 over molar to the 6 times days. Then from here, I wrote my complete rate law. And the last step was just to plug in these concentration values that were given in the initial problem to find the rate associated with those concentrations, right? So my rate came out to 7.22 times 10 to the negative 5th molar per day. Okay. Are there any questions on this problem? Okay, I also don't have really an activity for tonight, just because I knew we'd be talking about material for a while. So if you don't mind in the chat signing in with your net ID, and that will also just kind of indicate to me that you don't have any questions on these challenge problems. If not, I'll kind of be waiting for those questions. Before moving on, we're just going to cover the last few topics from this chapter, which corresponds with the second video in the folder kind of due this week, right? The second lecture video. I wouldn't anticipate, and I never like to say what you would and wouldn't see on an exam because I truly don't know. I would predict that this is harder than you would see on the exam, but do you all have the capacity to solve this problem? Absolutely. And so they could. However, if you have to solve one of these problems by creating a novel synthesis, I expect you to only have 2 reactants. Okay, so that's more similar to Monday's problem. This one's a little more complex because we have 3 reactants. And so would I bet I wouldn't expect this problem to be on the exam, but it is a fair question, and if they wanted to give you this problem, they definitely could. Okay, but again, for a novel synthesis problem, you'd probably expect to see 2 reactants. Okay, I think that's the only question I kind of saw. And so, sorry, I forgot. I have one more example to go through. So this one wasn't a challenge problem. I just promised on Monday that I'd bring up a first order example just to kind of talk about why professors love them so much. Right, and so we'll quickly go through this, and then we'll talk about catalysis and activation energy. Right, so you have a lake in your town that has a radioactive isotopes. It takes 4.33 days for half the isotope to break down. So that's just telling you your half-life is 4.33 days. After some tests are run, authorities decide to shut down the lake until the concentration decreases to 1/100th of a percent, right? So not 1%, 1/100th of a percent, so 0.01% of its current concentration. How long will it take for the lake to be reopened? I wrote this problem specifically to test for a first order reaction, so I didn't actually tell you that this is first order, but I meant to. Okay, so I did not indicate in this paragraph that this is a first order reaction. And I should have. Okay, so if you're worried, how do you know this is first order? I did a poor job writing this problem. But let's assume it's first order. How long will it take? Okay, and so you might notice how little information I gave you in this problem, right? Again, I would have had to tell you it's first order, but beyond that, I told you the half-life, and I gave you a percentage of how much is left in terms of concentration, right? I never gave you an initial concentration at all. I told you that you just had 1/100th of a percent remaining when the lake can be reopened. Okay, so I really only gave you 2 pieces of information. And the reason why professors love first order reactions, and this is typically what you'll see a little bit more often on exams, is because they can give you so little information, right? So the half-life is 4.33 days. We plug this in our half-life formula, and we can find our K constant right away. So K, in this case, equals 0.16, okay? Now, 1/100th of a percent is 0.01%, which, if you plug it in as a fraction, is 1/10,000, okay? And you'll often be given your concentration change in terms of a fraction in first order reactions, right? So what they're saying is you basically have 1/10,000th of what you used to have, okay? And so delivering information in this fraction way prevents them from having to give you your initial concentration, right? So again, they can just give you so little information, okay? Once you know it's first order reaction and you write the integrated rate law, you can reorganize this rate law, which is pretty much how you'll always reorganize it. The natural log of A over A naught equals negative KT. And again, they'll usually give you fractions. In this case, I just gave you a percentage that I wanted you to convert to a fraction, but they'll give you this fraction because you can just plug it right in for this ratio of A divided by A naught, okay? And so you take the natural log of 1/10,000, because that's your ratio of A over A naught, is equal to negative K, which we solved for above, times T, and you can quickly solve for T. It would take about 57.5 days for your concentration to drop to 1/100th of a percent of the original concentration. Okay, any questions on this before moving in to the about 3 topics that we're going to cover tonight that finishes out the chapter? Okay, if there are no questions, I'm just going to start with collision theory, right? So there's a basic equation behind collision theory, which is basically just talking about how we derive this K constant, right? So K here is what we see in the rate law, right? Our rate law constant, and it's equal to P times Z times F. Okay, and this equation itself doesn't really matter in terms of the actual letters, but what is important is what we're learning from these variables, what they represent, right? So K again is has 3 things contributing to it, right? The first one, P, stands for steric factor, right? And it basically accounts for the fact that successful reactions require certain orientations, right? So maybe molecules will collide together 10 times, right? But that doesn't necessarily mean it's going to be a successful reaction, right? It needs the correct orientation of these reactant molecules in order to convert to products, right? So if only one of the 10 collisions results in a successful reaction due to the orientation, that's what P will account for, right? Basically, how many of my collisions have the correct orientation, okay? Z stands for collision frequency, and as I'm sure you can kind of gather from that, it's really just how often do I have collisions, or how many collisions do I have in a certain amount of time? Okay, and so not only does collision frequency depend on length of time, but also concentration, right? As your concentration increases, your collision frequency will also increase because there are just more molecules in the system. Okay, the last component of collision theory is F, which is collision energy. And it basically stands for the fraction of collisions with enough energy to undergo the reaction. Okay, so basically, what fraction of my collisions have the activation energy or more energy, okay, which actually allows me to convert to products. Okay, so again, K is made up of 3 factors. Basically, orientation, is the orientation correct? How frequently are our molecules colliding and trying to react? And then lastly, how many of, what fraction of these collisions actually have enough energy to undergo the reaction at hand? Okay, now collision theory, again, the actual equation isn't something typically brought up, but I would definitely expect to see 1 to 2 theoretical multiple choice questions on it. Okay, this is important to understand. Okay, but again, it's not like you have to calculate anything from it. Just kind of note the factors that play into K. Okay. Now I want to comment on some equations. So this first one, I'm just going to call the CC equation so that I don't completely butcher it, which I'm sure you guys are now familiar from laboratory, right? And so in this equation, we can basically, it's similar to this equation below, the Arrhenius equation. But basically, we're taking the natural log of 2 different K constants that we get from 2 different temperatures. Okay, so if you're ever given 2 different temperatures or 2 different K constants, it doesn't really matter. Some combination of those, you can plug them in to this equation, right? And basically, you could graph this in order to find your activation energy. So EA is activation energy, right? K, these are our rate constants. R down here, I would really maybe underline or circle it. Realize that this isn't an equation where we have activation energy, right? Activation energy is an energy which is measured in joules or kilojoules. Okay, the fact that we have an energy in here should automatically indicate to you that this R constant has to be that 8.31 joules per moles Kelvin, I think is the units, right? It has to be that R value, right? Because if we have joules or kilojoules in the numerator, we need to have joules or kilojoules in the denominator. Okay, so that's just one thing I wanted to note. And again, you use this CC equation when you have 2 different temperatures or 2 different rate constants. Okay, and this CC equation is derived from our Arrhenius equation. Okay, so the Arrhenius equation says that our K constant is equal to A, which is known as our frequency factor, times E, right? That's a mathematical value. I think it might be like 2.7 something, right? But it's on your calculator. It's A times E, and then it's E raised to the negative activation energy divided by R, which is the same R as before. Oh, sorry, I wrote units here because I had to look up the units. I didn't remember them, and I forgot to input them, so I apologize. But activation energy divided by R times T, our temperature needs to be in Kelvin. Okay, and I'm just going to go back to the last slide, okay? But look at this Arrhenius equation. K equals A times E, and E is raised to the activation energy over RT, okay? Now the collision theory equation says K equals P times Z times F, okay? And if we look at F, which is collision energy, right? It has to do with energy, right? So it's the activation energy portion. Okay, so when we take this collision theory, right, we can actually find numerical values of collision theory using this Arrhenius equation. Okay, and so the E raised to the negative EA over RT is alluding to this F portion in our collision theory, right? This F portion in Arrhenius reaction is expressed by E raised to activation energy over RT. While the P times Z portion of our collision theory is accounted for by A, our frequency factor. Okay, and I'm going over this because you will see something like that in tonight's challenge problems. And again, that is a theoretical point that you could see in a multiple choice question as well. Okay, you can also, coming back to the Arrhenius equation, if you take the natural log of the entire equation, it comes out like this, right? Which might look somewhat similar to the CC equation, right? And the value of setting it up like this, the Arrhenius equation, is that it's actually in y equals mx plus b form. Okay, and so you can graph along the x-axis 1 over time, temperature, sorry, not time, temperature. If our y-axis is natural log of k, then we have a y-intercept equal to the natural log of a, and we have a slope equal to the negative activation energy over r. Okay, so it's pretty common for them to say that you graph 1 over temperature and natural log of k to produce a linear slope. They'll give you some numerical value for the slope, and they will say, what's the activation energy, right? And so you can solve for that kind of using the y equals mx plus b format of this. Okay. Some more theoretical notes. So we talked about activation energy and how that's the energy, you know, in terms of collision theory. So what is activation energy, in case you're a little bit unfamiliar with it? So really, it's the energy required to convert reactants into products. Okay, and so this energy diagram here shows the energy of my reactants, the energy of my products, and you'll see that the path taken, right, I start at my reactants and I actually go up, and at the highest point, we're at what we call the transition state, right? That's the highest point, and then from there, to get to products, you know, we'll convert and lose a bunch of energy, okay? But in order to go from reactants to products, we have to basically climb up this hill, which is a hill of energy, right? And so this difference between the energy of our reactants and the energy of our transition state is our activation energy, right? If you have that amount of energy or more energy, right, your reactants will easily be able to convert to your products. But if you don't have enough energy, right, your reactants aren't able to make it to the transition state. And so if you don't have more, like if you have less energy than your activation energy, your reactants will remain reactants and they won't be able to become products. Okay, so this is what the general setup would look in general. If you add a catalyst, what happens is this hump section actually becomes lower, right? The activation energy becomes lower for your reaction, right? You'll notice that the catalyst doesn't affect the original energy of our reactants or products. All it does is lower the barrier, the energy barrier that is required to undergo this reaction. Okay, and so that's just kind of the last thing we're going to talk about is catalysis, right? So what do catalysts do? They speed up reactions, and how do they do that? They do it by lowering the activation energy, right? They don't change our starting or final conditions. It just changes the energy required to reach that transition state, okay? And again, if you were to think of it in terms of collision theory, it's affecting that F portion, which has to do with how many collisions have enough energy to undergo the reaction. Something else to think of, to know about catalysts is that they're never used up in a reaction, right? A true catalyst will be exactly the same in the beginning and end of the reaction. And then lastly, there's zero order, which professors kind of touched upon several times, meaning that if we change the concentration of catalysts, it won't affect the rate of our reaction. Okay, And so the last part of tonight that I want to do is just go over two different problems that kind of relate to these new topics. And so the first one, we have a first order reaction. We're given the half-life of some reaction at 25 degrees Celsius and the half-life at 73 degrees Celsius. And they're asking us, what's the activation energy, right? So this kind of indicates to me that we need to use that CC equation, right? Because we're given two different temperatures. Okay, so I start out by just writing my known information. So at time 1, I'm calling it, our temperature is 25 degrees Celsius or 298 Kelvin. Temperature 2 is 73 degrees Celsius or 346 Kelvin. And again, I wrote my half-lives associated with each of these temperatures. Now, half-life itself isn't very useful to us. But what we can do is use the half-life equation, which we know because it's a first order reaction, to solve for K, right? These are our rate law constants at each of these respective temperatures. Okay, so at 25 degrees Celsius, I'm able to find that my rate law constant is 0.01925, while at 73 degrees Celsius, K2, my rate law constant, which I'm writing as K2, is equal to 0.2772. Okay. Once I have these two rate constants, I'm going to write my CC equation. So natural log of K2 divided by K1 equals negative activation energy over R times 1 over T2 minus 1 over T1. Okay. And the thing that I want to mention here is be careful about where you place your variables, right? So K2, that top K value, will be associated with this first fraction, right? 1 over T2, while the K in the denominator will be associated with the temperature that comes second. Okay, so I plug in all my values that I had from above, right? My temperatures, which I knew, my Ks, which I solved for, and R is this 8.31 constant, and I can solve for activation energy. Now, when I solve for activation energy, I get 47,611, and the units of this will be joules, right? Because that 8.31 value is joules per mole Kelvin. Okay, so if I want to convert it to kilojoules, I just divide by 1,000, and so activation energy is 47,600 joules or 47.6 kilojoules. Either of those is an acceptable answer. Okay. Now the last example that I'm going to give is kind of a catalysis example. And so this says a first order reaction has a half-life of 1.45 hours when run at 35 degrees Celsius without a catalyst. When a catalyst is used in the reaction at this temperature, it is found to be able to decrease the activation energy of the reaction by a third. What is the half-life of the reaction with a catalyst? And assume the frequency factor A is the same. Okay, so the first thing I want to mention is these types of catalyst problems, I think, came up for the first time that I've seen last year. Okay, and they really liked these problems. They showed students 1 or 2 of them, and then it appeared on the exam. Okay, and so the fact that I know Dr. Katie went over one of these in lectures, and since this is a topic that, you know, kind of came to fruition last year, I do anticipate a problem like this to be seen again on an exam. I anticipate it more for a long answer exam, but could they also modify it to be on a multiple choice exam? Absolutely. Okay, so definitely note how I kind of approach this problem. The other thing I want to mention about these types of problems is I don't think they will ever give you one, and I'm going to be honest, I don't really know how you would even really do it if they don't say assume the frequency factor of A is the same for each reaction. Okay, every problem I've seen for a catalysis problem like this last statement has been there, that the frequency factor is the same for both. Okay, so it's a pretty good bet that that's how we'll also see it. Okay, so I'm going to start out by solving for my K, of my uncatalyzed reaction, right? So we're told that my half-life and it's a first order reaction, is 1.45 hours. So I plug it into my half-life equation and can find that at 35 degrees Celsius, my uncatalyzed reaction has a K constant of 0.478, and the units would be hours to the negative first. Now what I'm going to do is I'm going to take the Arrhenius equation, but the one where we multiplied the entire thing by the natural log. Okay, this is the form that we're going to want to use. Okay, and so from here, I just start plugging in my values. So K we just solved for, so the natural log of K is equal to the natural log of A, that frequency factor, and I'll come back to that in a minute, minus our activation energy divided by R. Again, remember that this R has to be the 8.31 value times our temperature. 35 degrees Celsius is 308 Kelvin. Okay. Now, in a problem like this, where they say, assume the frequency factor A is the same for each reaction, because it's the same from one reaction to another, we can really choose any value for A. Okay. And so what your professors will suggest, what I'll suggest, and definitely the easiest way to do this problem, is to assume that A is just 1. Okay, and the reason for this is that when you take the natural log of 1, it's actually 0. Okay, so you can almost just ignore this natural log of A portion. Okay, and you can ignore it because we're just going to assume that it's 1 for all of our reactions. Okay, so when I evaluate this and solve for my activation energy, it comes out to 1,889 joules, or 1.889 kilojoules, right? And this is again for our uncatalyzed reaction. Now, they said that the activation energy for our catalyzed reaction is 1/3 less than the activation energy for our uncatalyzed reaction. Okay, so we can solve for this by basically taking the activation energy of our uncatalyzed reaction and subtracting from it 1/3 that amount of energy, which really what you're doing there is just taking 2/3 of the activation energy of our uncatalyzed reaction. Okay, and so when we do that math, right, 2/3 times 1,889 joules, we get that the activation energy of our catalyzed reaction would be 1,259 joules. Okay, and remember that this is again happening at 35 degrees Celsius. Okay, and so what I'm going to do is I'm going to again write my Arrhenius equation that I've taken the natural log of the whole thing. I'm going to plug in 1 for my frequency factor A, right? I'm going to do that in all of these, which natural log of 1 is 0. Okay, and I'm going to plug in my activation energy of my catalyzed reaction that I just solved for. I'm going to plug in R, which again is that 8.31 constant, and my temperature, again, it's still 308. I found that the natural log of K is about -0.492, and when I solve for just K, it's 0.611. Okay, so now I found the K constant for my catalyzed reaction, but I didn't ask for what the K was, I asked for the half-life, right? And the half-life, again, this is still a first order reaction, so the half-life is equal to 0.693 divided by our K, which is that 0.611 value. And so we find that the half-life of this catalyzed reaction is 1.13 hours. Okay, and this makes sense, right? Because the half-life of our catalyzed reaction is faster than our uncatalyzed reaction, that the half-life of our uncatalyzed reaction, which makes sense because it should occur faster in a reaction involving a catalyst. Okay, are there any questions on any material I've gone over tonight? So I'm happy to answer them. I'm just gonna flick through these challenge problems. I don't believe so. Lizzie, I'll go back to that slide in a minute. But Lizzie just asked, going back to the first example, I thought the equation had T1 first. Maybe on your equation sheet, but if T1 came first, K1 was probably in the numerator. Okay, so I'd say check your equation sheet. If that's not the case, I'd ask you to see, is there a negative sign somewhere that isn't in my equation? Okay, so here's, I'm just gonna, if you need pictures of it, I'm gonna switch in just about 5 seconds. So just get it in quickly now. And again, Lizzie, I will go back to that slide after flicking through these. Here's another 2. So as you can see, I did try to make a bunch of theoretical questions. Okay, so Victoria, thank you for clarifying it. It says if there is a negative sign in front of activation energy over R, then T2 is first, I think. That is definitely right. And I think I've come into contact with this with students before, right? So, you know, whether there's a negative sign and the order of some of these variables, it can vary depending on just if they want negative signs or what they want the order to be. But what I'd say is just stay consistent, right? So I would probably, if I were a student, I would use how they write it on the equation sheet. And I would use that to solve my problems and just stay consistent like that. Yep, and Lizzie confirmed that. So awesome. I'm glad we found that. And then Victoria, to your first question, you asked, did I just pick the frequency factor to be 1? Yes, right? Because they say the frequency factor is the same in all those reactions, the catalyzed and uncatalyzed, you can pick any value. And Dr. Katie, when he does examples like this, always chooses 1, and I followed suit. It just, because the natural log of 1 is 0, it makes your calculations so much easier. If you picked a different value, maybe it would come out the same, I'm not sure, but in every catalysis question I've seen, you should always assume that frequency factor A is 1, okay? And again, natural log of 1 is 0, so you kind of ignore that section. Yep, of course. Okay, and so number 7 tonight is one of these catalysis problems, and so I would highly recommend trying that before next Monday's SI. And yeah, seek help early if you have trouble with it. This is a tough problem. I think this is, in my opinion, the toughest I could make one of these problems. I actually made this last year, number 7. And I took the formulas and all the data and I asked myself, what is the least amount of information I could give you for you to still solve this problem? Okay, so number 7 is very, very tough, but I definitely recommend trying it on your own before Monday's SI. But if you get stuck, that's okay. Again, if you can do number 7, you can probably do almost any single one of these catalysis-like problems. Okay, and that's all I have. So I'm just going to I'm going to stop sharing my screen and the recording. But as always, I'm happy to stay after and answer any questions or come back into the PowerPoint.